Hi, my name is Jeremy Lim, and I'll be presenting about key concept in my tutorial-style term paper for Advanced Computer Networks on fog computing. Fog computing architecture operates as a hierarchical and distributed system with three main layers: the edge layer, fog layer, and cloud layer. Each layer is equipped with distinct components and plays a specific role in ensuring efficient data processing, storage, and communication. The edge layer comprises of end devices such as sensors and actuators that collect raw data from their environment. These devices are often resource-constrained, lacking the processing power and storage capabilities needed for complex tasks. The fog layer is the centerpiece of fog computer architecture, acting as a bridge between the IoT layer and the cloud layer. This layer includes fog nodes, which are strategically distributed across networks and equipped with moderate computational, storage, and networking capabilities. At the top of the hierarchy is the cloud layer, composed of centralized data centers offering extensive computational resources and long-term storage. The cloud layer handles tasks that require substantial processing power and archival storage. Fog nodes are spread across diverse geographic regions, closer to the data sources they serve. They are strategically deployed, adopt a distributed network, and have a layered proximity. These fog nodes consist of gateways and routers that perform initial data filtering and aggregation before forwarding to the cloud. Or they can be edge servers that handle more intensive processing tasks. Some of the challenges fog computing faces are security concerns such as data transmission risks and heterogeneous environments, as well as management complexities such as coordinating and resource monitoring, and lastly, energy efficiency such as power constraints and fog nodes and heterogeneous and dynamic workloads. Next, I'll be presenting on the related works that address the above challenges. Firstly, to combat the security issue, this paper suggested the use of multi-factor biometric authentication for fog computing, where fingerprint, facial recognition, and eye scanners were proposed for verification before the user is granted access to fog computing services, providing a higher level of security. On the topic of security, the next paper suggested the privacy-preserving scheme with smart contracts and Quad 3 in 5G for fog-enhanced smart logistics to address the growing concern of data privacy leakages in the increasingly popular field of fog-enhanced smart logistics. It utilizes smart contracts to manage the generation, circulation, and processing of logistics data and achieves the key security goals of privacy preservation, unforgeability, traceability, and efficiency by using immutable smart contracts. Moving on to energy efficiency, this paper on energy-efficient fog computing for 6G-enabled massive IoT examines the critical role of energy-efficient fog computing in 6G-enabled massive IoT networks and highlights the need for innovative solutions to address the increasing energy demands of future networks. The paper provides a comprehensive overview of the enabling technologies of 6G networks, discussing how they will support massive IoT applications and thoroughly review various energy-aware techniques for enhancing energy efficiency in fog computing-based IoT networks. These techniques include energy-aware task offloading, energy-aware fog node placement, energy-aware device control, and energy-aware energy harvesting. The last paper deals with resource allocation in combined fog cloud scenarios by using artificial intelligence. It explored the limitations of relying solely on cloud or fog computing to meet the quality of service demands of delay-sensitive IoT applications, with the key challenges of identifying the optimal resource and efficient task distribution. The proposal was an artificial intelligence-based task distribution algorithm that predicts the processing time and result size for each incoming task using artificial neural networks, then distributes tasks based on these predictions and a predefined policy aimed at minimizing both internet traffic and response time. Based on the related works, we can see that fog computing is already present in many fields and has drawn considerable research interest. However, there's further emphasis on the integration of emerging technologies such as serverless computing, 5G, quantum computing, and federated learning as potential research directions for improving the challenges of fog computing. The development of new AI-powered or AI-integrated frameworks and methodologies that incorporate these emerging technologies is also worth further exploring to address the complexities and challenges of the evolving fog and edge computing landscape. Here's an example of how federated learning can be integrated into the fog computing architecture in smart cities where federated learning is done at the fog nodes, and the result is aggregated in the centralized cloud for energy consumption optimization and urban planning. Thank you.